Okay. Yes.
Okay, you can talk now.
Okay, well, boa tarde, good afternoon, everyone. Welcome to our seminars of the astronomy department at URGS. Today, we are having a guest, Sandro Tachele, from now in Korea, but former Center for Astrophysics at Harvard and Smithsonian. He completed his PhD at the ETH Zurich in 2017, and where he was also a research assistant before going to the United States. And as I mentioned, he's now in Korea, so we double thank you for accepting the invitation. His research interests include the formation and evolution of galaxies across cosmic time, by studying the physical mechanism that govern the formation and of the first galaxies in the early universe. Sorry, my English is not very good today. The buildup of the bulge and disk components in galaxies, and the cessation of star formation in massive galaxies. And today he's going to talk about the diversity of building up the quiescent sequence at redshift 1. So you can start when you're ready, Sandro.
Yes, well, thank you very much, Alejandro, for the very nice introduction. Also, Marina, for the invitation. So I'm very excited to give this presentation. And as we, just said, I'm in Korea at the moment, so it's 1:30 in the morning. So if I'm not very coherent, feel free to interrupt me and ask questions directly, or otherwise at the end of the talk. So as you have heard, I'm at UNIS now. This is the Ulsan National Institute of Science and Technology. UNIS was founded in 2009 and is one of the 4 public universities in Korea that focus mainly on research in science and technology. And it's an English-speaking university, so all the courses are taught in English, and so the faculty and the students are very much, international in outlook. And so I've been now starting there the extragalactic astrophysics lab. And so it's very, we just recently started in this summer. And the research that I want to do in the next few years mainly focuses on the observation evolution of galaxies. It's both observations and theory. I will focus mainly on observational side today, but I will also add a few, theoretical investigations that we've been doing over the past few years and also currently are doing at Harvard and at UNIS. So what are the topics that I'm very much interested in? It starts out with the regulation of star formation in local galaxies and in kind of local scales within galaxies, but also on large scales when we think about the environment of galaxies. I'm very much interested to understand the buildup of structure in galaxies, disk and bulge components, and this not only at low redshifts, but all up to high redshifts. And so that's links directly to the topic of the formation of the first galaxies and the connection to ionization. Here, of course, the James Webb Space Telescope is the big topic at the moment that I will be touching on at the end of my talk. We are also developing and analyze analytical and numerical models to understand the observations that we are performing. And in particular, today, I will be focusing on the quenching of galaxies. So this means the cessation of star formation. And I will mainly focusing on this. But if you're interested in any of the other topics, I'm, of course, happy also to talk about those. So let me start with a brief introduction into galaxy formation and evolution. So we have a quite good understanding of the initial conditions for galaxy evolution, thanks to observations such as the cosmic microwave background, the CMB, which shows us basically a map of the universe roughly 400,000 years after the Big Bang. And so what you can see here are these tiny fluctuations in temperature, which then correspond to fluctuations in the matter distribution in the early universe. And so here, basically what you see here is the temperature fluctuation, angular power spectrum from this map here. So the red points are the data points from the Planck satellite. And the green line shows you our best fit model, the lambda CDM model, where lambda stands for the cosmological constant and CDM stands for cold dark matter. And so you see that the data is very well fit by this model. And so this model tells us that most of the energy budget today in the universe is dark energy. And then the matter component is dominated by dark matter. And the ordinary matter, the baryons, are only making up about 5% of the total composition of the universe. So if we now, at the moment, just ignore the baryonic matter and just think about dark matter, we are able to actually solve gravity very well on large scales. And so what we do is we run these n-body simulations to predict the large-scale structure in the universe. And so what I show you here is from the Millennium Simulation Project. These are basically showing you the cosmos on the largest scales, shows you the cosmic web. So you can see the distribution of dark matter. You see the filaments, you can see these knots where we form dark matter halos, and the very brightest regions are where galaxy clusters are forming. And so what has been found is that the very much observations of the early universe can match up these local observations of the distribution of galaxies very well when we have a cold dark matter universe. So you see here the redshift measurements of basically local structures. This is from the CFA redshift survey, and then we have the slow one and so on. So we have the redshift distribution of the galaxies close by, and this matches very much what we see in such n-body simulations where we assume a cold dark matter universe. So let's say we have a good understanding of the cosmology of the dark matter, but then when it comes to galaxies, it gets actually more complicated. So when we assume this very simple paradigm for galaxy formation, where we have the formation of dark matter halos, so we have the growth of dark matter fluctuations in the early universe, followed by dark baryons that are cooling in these dark matter halos and form stars, we see that we need some kind of feedback, some kind of regulation of star formation via stars and black holes that prevent overcooling. And so this can be seen in different kinds of observations. For example, we can look at the number density of objects as a function of mass. So what I show you here is the number densities of galaxies as a function of stellar mass. So the blue shows you the galaxy stellar mass function. This is the typical Schechter function. We have here power law slope and then an exponential cutoff at high masses. And when we now compare this to the number density of dark matter halos, we see that they are quite inconsistent with each other, right? So what I show you here as a red dashed line is the dark matter halo mass function. Now here, we basically rescale the dark matter halo masses by the baryon fraction, by the cosmic baryon fraction, which is roughly 16%. So when we do this, we see that yes, the number density of galaxies, around 10 to the 11 roughly matches what we would expect from the number densities of dark matter halos. But we see that somehow at low halo masses and at high halo masses, galaxy formation is less efficient. So we have somehow suppressed star formation both at low halo masses and at high halo masses, so that we are able to go from the dark matter halo mass function to the galaxy mass function. Another way to see that we have to regulate star formation is when we look at the color distribution in the galaxy population. So what I show you here is the U minus R color. This is thus corrected as a function of stellar mass. This is work from Kevin Chawinski from the SDSS survey. You see that the galaxies are forming this bimodal distribution. We have blue galaxies down here. These are mostly star-forming disk galaxies. And then when we go up here, we have a red sequence. We have mostly red galaxies here. And you see that this is this shows you already that somehow we have star-forming galaxies and they need to somehow transition to form the red sequence. And when you think about the buildup of dark matter halos, it is actually counterintuitive such a scenario, because when we look at the dark matter universe only, we see that the most massive structures actually formed most recently, right? We have this bottom-up scenario where small structures form first and they merge to form larger structures. But when we look at here, right, we see that actually the most massive galaxies are the reddest galaxies that have little star formation and have actually the oldest stellar populations. So again, this means that we somehow need to suppress the star formation activity in these most massive halos. And so this means that we need to somehow quench the star formation in these objects. So how can we do that? What is the physics that governs the baryonic physics? Or what's the baryonic physics base? So on large scales, again, I want to give you a bit of an overview of scales first. We have the cosmic web. We have these small, filaments. We have the knots. So we have the dark matter halos on megaparsec scale. We can zoom in the very centers. We have these galaxies forming on kiloparsec scales. But then when we are interested in star formation, this takes actually place on even smaller scales, right, on the parsec scale. And you can see here that we have these young stars that are then acting on the surrounding gas and basically, dilute the molecular clouds again and destroys the molecular clouds. But we also know that most of the galaxies today have actually a black hole in their core. And so in the very centers of most galaxies, we have clear indications for some form of a black hole. And this shows you an image from the accretion disk around the black hole from the EHT collaboration, from the Event Horizon Telescope collaboration. And so I mentioned here a few physical processes that are working on these different scales, right? We have the black hole growth, which of course takes place on very small scales, but the black hole activity is afterwards reflected on very large scales, where we can look at, for example, the Fermi bubble in the Milky Way. We have the formation of stars in molecular clouds. These stars explode. There are supernova explosions, but there are also solar winds that act on the surrounding gas. We have radiation fields from the stars, but also from the black hole. We have the interstellar medium that is typically multi-phase. We have the cold phase, warm phase, and the hot phase in galaxies and around galaxies. We have the formation, the fusion of cosmic rays that might play an important role of how the stellar feedback actually acts on the surrounding gas. We have magnetic fields in galaxies, and then also we have gas flow and cooling, of course, on older scales. And so the complication here now, again, is that we have all these different physical processes that are acting on a wide range of different scales and coupled together. And that's why it's very difficult from a theoretical point of view to build up an ab initio model where we basically put in all the ingredients and just solve them, right? Because it's computationally very, very expensive to, at the same time, basically resolve an accretion disk around a black hole and the large scale environment of a galaxy. And this is until now basically impossible to resolve in a numerical simulation. And so we are typically implementing what we call subgrid models. So basically ad hoc numerical recipes so that we can account for these different processes on these different scales. So what causes quenching in massive galaxies? What are kind of theoretical ideas? And I'm going here very brief and very quick over it. So when we think of galaxies basically sustaining their star formation through fresh gas, right? So we have some kind of a fresh gas inflow. We have the formation of molecular clouds. We have then star formation. These stars will return some of the gas back into the galaxy, but also drive outflows. When we think about this simple regulator model, we can see that we can suppress the star formation in different ways, right? So one obvious way is to, for example, say, well, let's stop the inflow. And this you can do, for example, through cosmological starvation or a viral shock in the dark matter halo. But you can also think about heating the gas in the halo, for example, via an AGN or via gravitational heating. There's also the way that you stop or you prevent the cold gas from forming stars. This can be, for example, through morphological quenching by having a massive bulge in the center. But there are also more exotic scenarios, for example, through magnetic fields. Then you can also think about ways to, sorry for this, you can also think of ways, for example, to rapidly consume the cold gas. You can have, for example, a galaxy merger. So two galaxies collide, which will then compress the cold gas, and a lot of stars will be formed in a starburst. And this, this formation of new stars, but also the outflows of the stars will then basically consume all the gas, and there will be no gas left over. And finally, the gas can, of course, also be removed via stellar feedback or also via black hole feedback, via AGN feedback, which pushes out the gas in galaxies. And so again, I cannot give you now a detailed timescale for all of these processes, but you can see that the probably timescales will be an important driver in understanding which processes are important. So for example, when you think about an inflow, then you still have some gas left over, so the star formation will quench on rather slow timescales. But if you're removing the gas very quickly, right, then what happens is that the star formation will be basically instantaneously suppressed. And so the goal now on the observational side is to understand how quickly actually galaxies quench their star formation. And so this is the main topic of my talk in the next 30 minutes or so. And so I already hinted at it, but why is progress difficult to understand the quenching of star formation? And I mentioned to you just before that it's physically a hard problem because there are many different processes that are coupled on an enormous range of different spatial and temporal scales. So this is making it physically a difficult problem. But when you think about the literature, there is also a wide range of different definitions of what we actually mean with quenching. So what do we mean with a reduction of star formation? What is the physical unit of this? It's also difficult to compare actually observations to theoretical models. You can see this here. So I'll show you here a wide range of different numerical simulations that are able to produce realistically looking galaxy populations on like the 100 megaparsec cube box simulations. This is IllustrisTNG, this is the Simba simulation, this is the Eagle simulation. And what is shown here are basically different predictions for how quickly galaxies quench their star formation. And again, these different works have used different definitions of what they mean with quenching. But even if you have these measurements, for example, of the quenching timescale, the simulations refer to a quenching timescale that is probably quite different from the observation. So it makes it very difficult to then take just these numbers and compare to what we measure as a quenching timescale in the observational space. And then finally, there is, of course, when you think about the observations alone and want to forget about the numerical models, there is a limitation in observations that we cannot really see how an individual galaxy quenches its star formation, right? Galaxies, to us observers, basically stay the same because the dynamical timescale in these galaxies is so large in comparison with our observational time. And so we have a very hard time to really infer quenching timescales, as you will see throughout my talk. So what's the outline, right? So the key question I try to address is really, how do galaxies leave the star forming sequence and cease their star formation? And what is the timescale for this transition? And the steps, is basically I will go into the definition of quenching a bit because I think this is very important so that we are all on the same page on that. Then I will focus on galaxies around redshift of 2, so the galaxies that lived 10 billion years ago. And we try to see how galaxies look when they are in the process of quenching. And then I will focus around redshift 1 onto an archaeological approach where we basically look back onto the epoch of quenching of galaxies. So let's start with the definition of quenching. And I'm here quite generous in the sense that I say, well, quenching I define to be the transition from being star forming to being quiescent. And so here quiescent means that you are in a state of negligible stellar mass growth due to star formation, right? You can still grow in mass when you're quiescent because of mergers, but I define quiescent to be the state where there is no more star formation with respect to the stellar mass that is already present. And so this can be physically expressed with the specific star formation rate, right? This is the star formation rate divided by the stellar mass. And so this is basically the inverse of the mass doubling timescale. You can see this here when you are now, solving for the mass and integrating this. You see that here in the exponential, you just get the specific star formation rate times time if you assume a constant specific star formation rate. And so this means that the mass doubling timescale, so the time it takes to double your mass, is directly proportional to 1 over the specific star formation rate. And so this now, if you want to define quenching or quiescent, right, you basically see that the mass doubling timescale is much longer than the Hubble time at this epoch of observation. So you can think about this, that you maybe still have some residual star formation, but this star formation doesn't really anymore contribute to the stellar mass growth within the Hubble time, within the age of the universe. There are also other definitions. For example, you can use color, and I showed you the color mass diagram before. You can also use slightly more sophisticated color definitions, such as the UVJ color cuts. You can also cut relative to the star formation sequence, as I will show you shortly, or you can assume a star formation equal to V0, but this last definition is not very useful because, as you will see, that in observations are only able to determine upper limits when it comes to star formation rates. overall, but especially when you think about the UVJ cuts, they are actually very similar to these specific star formation rate cuts. There is maybe a disagreement on the 20% level, as we have shown in one of our recent works. So when we look at the distribution of star formation in the galaxy population, right, and what I show you here is basically today, this is going back in time. Down here, we plot the units of redshift. So what we see is when we look at the cosmic star formation rate density. So this is the star formation rate density in a co-moving volume as a function of time. You can see that the first stars, formed around the redshift of 10 to 20. And this is something that we want to figure out with JWST in the upcoming years. And then what you can see is basically an increase in the cosmic star formation rate density, which can be understood by an increase in the number densities of galaxies that are able to form stars efficiently. So you can see that these galaxies are forming more and more stars more and more efficiently. And also there are more and more such galaxies. And then we have a peak around redshift of 2. So about the look back time of about 10 gigayears or about 3.5 gigayears after the Big Bang. And afterwards, the cosmic star formation rate density has been dropping. And again, this is a combined effect of having lower accretion rates onto dark matter halos. So the specific star formation rates in galaxies are typically lower, but some galaxies also fully quench their star formation. And that's why we have this lower cosmic star formation rate density in most recent epochs. Now, we can also split this, and basically look at the specific star formation rate as a function of mass, as a function of redshift. And this shows you different literature compilations. This is from redshift 0, from Samir Salim's work, matching GALEX to SDSS to WISE. And here we use 3D HST data. And what you can see is basically there is this population of star-forming galaxies, and then we have this second cloud of points. And what I want to stress here is that this is not really a sequence. It looks like a sequence, but you have to think about this. These are more like upper limits of specific star formation rate measurements. What happens here is basically that we are not able to really measure specific star formation rates below about 10 to the minus 13. And so galaxies start to cluster around this limit here. But you should think about this, that, that these galaxies might lie at even lower values. Now, another thing that you see here is what we call the star-forming main sequence, right? So at all epochs, you can see that there is a relation between the star formation rate and the stellar mass in galaxies. And in this, in this space here, between the specific star formation rate and the stellar mass in galaxies. And you can see that this relation, slightly increases, right? Normalization of this relation increases with time, with look-back time, so at earlier times. And again, this can be understood because higher molecular gas fractions, because higher accretion rates in galaxies at early times. And so what I want to highlight now is if we now plot lines of constant doubling timescale, right? So this is now specific star formation rates. This means that now we can plot lines of how long it takes for galaxies to double their mass. And you can see that galaxies basically on this blue line take about a Hubble time to double their mass. Galaxies down here take about 10 Hubble times to double their mass, and galaxies down here take about 100 times to take 100 Hubble times to double their mass. And so you see that basically, yes, galaxies up here, they are still happily forming their stars, but galaxies down here, they are not forming stars very happily anymore, right? Their star formation rates are so low with respect to their stellar mass that this star formation doesn't really contribute anymore to the stellar mass growth. And so we can say that these galaxies are quiescent. And interestingly, you can see that the galaxy population moves slightly more above this blue line, meaning that galaxies at higher redshifts were doubling their mass quicker with respect to the Hubble time. Another way to show this is basically when we now wait for a Hubble time and ask, well, how much did these galaxies increase their stellar mass? We see that galaxies, here, okay, if we wait now for 14 gigayears, right, these galaxies would have grown by this much, right? So roughly by 0.3 dex. So they would have moved from here to here. But galaxies that are staying here, they are actually only has, if you wait now 14 gigayears, right, they would have only moved by that much. So this means that, galaxies are not able to move really from this diagram, from the upper left here to the bottom right here anymore, right? They have a very hard time to move to the right in this diagram because the specific star formation rates in today's universe are so low. And so this means that when we look at disk galaxies today, right, these disk galaxies have so low star formation rates that they will not be able to move to the right in this diagram. They will not be able to form these elliptical galaxies that we see, the most massive galaxies. So there is no link between these galaxies. So the question then is, of course, well, how do these massive elliptical galaxies then form, right? They are not, what are the progenitors of these galaxies? And so the main takeaway here now is that, well, the progenitors of these galaxies are actually galaxies at much earlier times that were star forming. So these galaxies look quite different. And I will be focusing now in my second part of my presentation on the objects here. So what do I do? Well, we do now basically focusing on these redshift 2 galaxies because we think that the most massive galaxies in today's universe have been star forming back in time. And again, at the peak of the cosmic star formation rate density at around redshift of 2 or 10 gigayears ago, it's where most of the stars in the universe have formed. So this is for sure a very interesting epoch to understand how massive galaxies have building up their stars and their stellar mass. And this is also something you can directly see when you look at the stellar mass function, right? So this is showing you the mass function now at different epochs, right? I showed you before just the redshift 0 mass function, but now we can look at it as a function of time. And so you see that at early times, most galaxies were actually star forming, and the quiescent galaxies were in the minority. Basically, there were very few quiescent galaxies. But then only going one step in redshift, right, going from redshift 2 to redshift 1, you can see that the quiescent galaxies have really been building up significantly, and the most massive galaxies are already dominated by the quiescent galaxy population. And so this indicates already that around redshift of 2, many galaxies need to transition to the quiescent population. And so this is what I'm focusing on now. So this framework that has been established over the last 15 years or so is what we sometimes call the grow and quench framework. And so we think that galaxies grow on this relation, the star forming main sequence, right? I showed you before that at a given stellar mass, there is this specific star formation rate that is typical for galaxies. And so this shows you now basically kind of a cartoon diagram of how we think galaxies move along such a relation with time while they are building up their mass. And so I don't have too much time to discuss this. I'm happy to talk more about that. We have done quite a lot of work on understanding how galaxies are building up their structure while they are star forming and how they're building up bulges while they are on the star forming main sequence. And in particular, in recent times, we also try to understand how galaxies actually fluctuate around this main sequence, because these different processes, these different physical processes I mentioned, they will be imprinted on these fluctuations as well. And I'm happy to talk more about this if you're interested. What I want to focus on now is basically this forward approach to measure quenching timescales, right? We have these star forming galaxies and they somehow have to quench their star formation. And what we hope to do now is by looking at massive star forming galaxies to observe quenching in action and to measure the quenching for the star formation. Sorry, yeah. What is a downside of this approach, right, for measuring the quenching timescale in this way? Well, the problem is that it's difficult to predict the future, right? We can maybe see some signature for quenching, but we are not able to wait and see how the full galaxy quenches its star formation and basically really follow the galaxy being here to go down here. And so this is a caveat in this analysis here. So let's focus on this. So the data set that I want to very briefly introduce is the SynfZ survey, which is the largest adaptive optics space resolved survey that we have been conducting over the last 10 years or so. And I've been leading the Hubble Space Telescope follow-up of this survey. And so we have been taking images of galaxies such as those here, right, close to AO guiding stars. And this is a Hubble image, and it's pretty cool, right? Because you have to imagine this galaxy now is around the redshift of 2. It's slightly above redshift 2. So these photons have been traveling for 10 billion years. And today we are able to see these galaxies and use different filters to map out the stellar populations in these galaxies. At the same time, thanks to IFU observations with Symphony, we are able to map out the H-alpha emission line. We are able to measure the flux distribution, but also the velocity, distribution in this galaxy. So we can see the kinematics, so which part of the galaxy is moving towards us and which part of the galaxy is moving away from us. And so the measurement that I've been mostly interested in is understanding where are the young stars in these galaxies. And so what we are able to do is to map out the older stellar populations or the stellar mass distribution in these galaxies. These are now very massive galaxies. And we found that these galaxies have very high central densities, and their Cersei profile is typically an N of about 3. So they have very clear indications for kind of bulges in their cores. Whereas when we look at the H-alpha distribution and infer the star formation rate distribution, we see that these galaxies have typically kind of a disk component. And so if you are now looking at the specific star formation rate distributions, now this is now spatially resolved, right? This is specific star formation rate as a function of radius. We see that when we look at lower mass galaxies in our sample, we have on average flat specific star formation rates. This means that these galaxies are doubling their mass at all radii with the same pace. But when we look at the most massive galaxies, right, we see that they have a reduced specific star formation rate activity in their core relative to the outskirts. And in particular, when we look at the numbers, we see that the specific star formation rate inverse, or the mass doubling timescale, is longer than the Hubble time in the core. And that's why we call these galaxies having quiescent centers, kind of mature bulges, quiescent centers, while they still have a star forming disk component. And so we think that these galaxies quench from the inside out. What I show you here is the stellar mass density distribution for these galaxies with respect to redshift 0 observations. And you can see that the stellar mass densities are very consistent between, basically between the redshift 0 observations and the high redshift observations. So this means that the galaxies cannot keep forming stars for very long in their cores, but they need to quench their star formation very soon, and then they have more time to keep forming stars in the outskirts. And so now this should be a movie, but it seems not to play. So let me try to exit that and maybe play it in this way so you can see this. So this is basically when we think about that we want to build up the stellar mass, but not overshoot the redshift 0 constraints on the stellar mass density profiles in early type galaxies. So you can see that we can form stars in their center, but only for a short time, but keep forming stars in the outskirts for longer. And so we are then able to infer what we call like a quenching time scale as a function of radius. And we see that these galaxies quench from the inside out. So what do we see in these galaxies? Well, when we look at the very core of these galaxies, we can see some signature for very powerful outflows. I show you here for the H-alpha emission line, we can measure the width of the H-alpha emission line. And what we see is that the width is implying full width half maxima for low mass galaxies in the nucleus and in the disk, of about 300, 400, 500 kilometers per second. But then when we go to these most massive galaxies, we can see that only in the core, right, only in the nucleus of these galaxies, we find very broadened components. We find outflow velocities of about 1,500 kilometers per second, whereas when we're in the disk, we still have rather narrower widths. And so this seems that there is some kind of black hole activity in their cores, but we cannot really see the X-rays or something, right? It's not like at the redshift 0 where these things are very bright in the X-rays. So we can just see that there is a broadened component in the centers of these galaxies. So the black hole might play a role in quenching these galaxies. What do models say, right? So we can do basically comparisons, for example, with the IllustrisTNG model. And we have published earlier this year with Eric Nelson some nice work on looking at the IllustrisTNG 50 model. And in this model, at least, it's clear that this inside-out quenching can be reproduced, but only if you have a black hole active. If you don't have a black hole active in these simulations, you switch off the black hole, you are getting flat specific star formation rate profiles. So clearly in these simulations, this inside-out quenching signature implies kind of an activity of a black hole. But we also have done work with other simulations, with, for example, the zoom-in simulation VILA, and there we are able to get very consistent quenching timescales as a function of radius by having no HCM feedback invoked, but there you get inside-out quenching because of kind of a starvation process where you basically suppress the feeding of gas, in the central region. And so you are suppressing the star formation activity there because of this, and you have still some star formation in the outskirts. So again, it's not very conclusive yet, and I think more work needs to be done on this. And so I don't have, I think, time for discussing sizes. I'm happy to talk about this if you want. But another way now to look into this problem is actually going the reverse approach, right? Basically looking at galaxies that are quiescent and try to understand over which time scale did they shut down their star formation. So you're basically going this way, right? You're looking at these galaxies, and by measuring the stellar populations, you apply an archaeological approach and try to see how quickly they suppress their star formation. And so the good thing with this is, of course, that we know that quenching happened. The bad thing is that there is a mixing between in situ and ex situ component, right? So we can see that, for example, maybe we have two galaxies, one quenched early, one quenched late, and then later on they merged. And now we are measuring the stellar populations, and we try to infer the star formation history and the quenching timescale. What we get is a mixture of both galaxies. And so what you want to do to basically make sure that this problem is not very important is you want to go to as close to the epoch of quenching as possible, right? And so that's how we are doing this analysis at redshift of 1 and not at redshift of 0. And at redshift of 1, we also have more information about the recent star formation because the spectra and the photometry includes more information about the most recent star populations than when things happened 10 gigayears ago. So the sample that I've been working on over the last year is the Halo 7D survey. And this is actually a very nice collaboration between people studying the Milky Way halo and people like me who are interested in the background galaxies. And so this survey is focusing actually on, measuring proper motions of 1,000 stars and getting radial velocities. And so it uses HST together with Keck. And so we are interested in particular in these very deep spectra that we get out of it. So we get, for these filler objects, for our background galaxies, integration times at Keck of about 8 to 32 hours. And so this means that we have very high signal-to-noise spectra of the order of 20 per angstrom or higher. And so the specific sample that I'm focusing on is it's about 160 objects with very high signal-to-noise spectra, very comparable to Legacy at the DLT that you might have heard of. And so this focuses mostly now here on quiescent galaxies, as I mentioned, around redshift of 1. But we also have a few star-forming galaxies in our sample. And so here I want to briefly introduce you now how do we infer the stellar populations for these galaxies and what is the analysis technique. And what we're doing is a full spectrum fitting, and we are using Prospector for this. And the strength of Prospector is that it's fully Bayesian, and it allows us to rigorously combine photometric data and spectroscopic data. We have a 20 to 30 parameter model, so this sounds quite extensive, and I very briefly introduce you to some of the core parameters here. We have standard things such as redshift, solar mass, velocity dispersion, metallicity. We have dust emission, dust absorption. We have HEN emission. We have non-parametric star formation history. This means that we have a flexible star formation history. We don't have a parametric shape with time. We can basically fit 10 time bins that are variable. And we have emission lines that we self-consistently model. And we also have an outlier model to take care of skyline residuals that we might not have properly subtracted in the spectrum. So, I shall show you here an example for how this data looks like. So these are quiescent galaxies now, right? They look much more boring than the star-forming galaxies at high redshifts. But here you see the nice photometry, right? These are basically these famous deep fields. So we have photometry all from the UV to the infrared up to 24 micron MIPS with Spitzer. And we also have now, just in this range, actually, the spectrum, right? But the spectrum, of course, contains a lot of information. We have all these nice absorption features, the Balmer lines, but also the metallicity lines and so on. So you get a lot of information from this. And then what we get from the Prospector analysis is the star formation histories, right? This includes now basically the full posterior, so it includes all the uncertainties in the metallicity and the dust attenuation and so on, and it's fully reflected here. And so again, we have the non-parametric approach, which means we have these time bins, and you can see that we have basically an increase in star formation history for this object, something like flat, and then a decrease in the star formation in the last giga-year or so. And again, because it's fully Bayesian, we also get the degeneracies between all the parameters, and we can do some nice corner figures such as here. I don't have time, I think, to discuss parametric versus non-parametric, but I'm very happy to discuss possible biases that you might get when you assume parametric star formation histories. As you might know, for us, it's very important to fit both spectroscopic and photometric data. The spectroscopic data alone gives you a biased result. Also, the photometric data alone gives you a biased result. So you don't really combine this. The key is that the older stars, of course, very well traced in the spectroscopic data, but the intermediate age stars, they are very well reflected in the UV, and so you want to use the photometry for that, right? So if you look, for example, at the light-weighted age as a function of wavelength for, you know, a star formation history that is decreasing slowly with time, your UV really contains age, you know, the light-weighted ages from 10 to the, you know, a few times 10 to the 6, all up to 10 to the 9 years. So you really want to include the UV in this analysis. And so what do we find? Well, you see, these are now basically selecting galaxies at redshift 1. And, you know, this shows you now as a function of mass, the formation redshifts. The formation redshifts are defined to be the redshifts where 50% of the solar mass was in place. And you see that basically at the fixed mass, we find this large scatter, right? There's this large diversity. And this is something that is also been seen in other data sets, in other surveys. And so it's quite, this is, I think, a very interesting statement that even if you select redshift and mass, you find a large diversity of star formation histories at, you know, of formation redshifts. The second important point here is that we find a population of very old galaxies. So some galaxies seem to have formed a lot of stars very early on in the universe. And I think this is very interesting for the James Webb Space Telescope, because the James Webb Space Telescope will be able to trace these galaxies and find these galaxies and really find the first quiescent galaxies in the universe. Now a bit more, you know, and maybe this is a kind of a detailed figure, but this shows you the star formation histories for all the galaxies in our sample. And so you see here that, you know, in each of these panels, the specific star formation rate as a function of lookback time. And this shows you redshift and mass for our sample. You can just, you know, pick up one diagram, for example, you know, this one here. And you can see that the red curves show you the galaxies that are quiescent at the epoch of observation. And these curves here, the solid and the dashed line, shows you basically, you know, the classification for star forming, transition, and quiescent galaxies. And so even if you select a rather narrow mass bin and a rather narrow redshift bin, and you are basically looking at quiescent galaxies, you can see that galaxies show a wide range of different histories. Some galaxies have transitioned very early on. Some galaxies have transitioned very recently. Some galaxies have transitioned very quickly, right? They very abruptly quenched, and some galaxies have quenched very slowly. And so I'm basically want to highlight that there is this large diversity of quenching histories in these galaxies. And we can now formally define the quenching timescale. So how long did it take for a galaxy to transition from the star-forming population to the quiescent population? So we see that we can, you know, define this basically as the time it takes for a galaxy to go from here to here. And so here I'm basically showing you now the quenching timescale, so how long it takes for a galaxy to quench and when the galaxy quenched. And this figure basically shows you that galaxies basically span the full allowed range, which means that we find galaxies that quench very early, we find galaxies that quench very late, we find galaxies that quench very slowly, and we find galaxies that quench very fast. And so it seems that we find a large diversity of quenching timescales and also quenching epochs, even though at the very, you know, at the fixed epoch of observation. Now the question is this reproduced by numerical models? And so here I basically have redone the same analysis for the numerical model. So I have taken Illustris, you know, the IllustrisTNG simulation. I projected these simulations into the observational space. I, you know, generated photometry, spectroscopy, added noise according to the observations. and I redone the measurements. And what you can see is that, yes, it's actually not too bad, right? We, get a significant spread, but we are clearly missing the outliers. We're missing galaxies up here. So we have not these very slowly quenching galaxies. And we also don't have the very early quenching galaxies. And so there seems to be, yes, to first order, these numerical models get the overall distribution right, but we are missing some of the outlier populations. And the caveat there is, of course, that the outliers are always difficult to model because we have finite volumes in the observations and also in the numerical models. Okay, so I think I have to wrap up soon, right? So I probably have only 3-4 minutes left. So I try to give you basically kind of a summary now, but I want to mention quickly Min-Chong Park's work, who is a Harvard graduate student, and she has been focusing now a bit more onto the simulations and understanding quenching timescales. And she finds that that we can produce quiescent disks, we can produce quiescent ellipticals formed via actually kind of secular evolutionary processes while they were quiescent. We find galaxies are able to form elliptical galaxies through mergers after they quench. And we also find formation of ellipticals through gas accretion while they were still, misaligned gas accretion while they were still star forming. And so the key conclusion there is that even an IllustrisTNG model that has a very simple black hole feedback model is able to reproduce this large diversity of quenching timescales and also the rich morphology because of the combination with a stochastic merger history. So this means that the galaxies quench in this model very simply, but because you can have mergers during quenching, before quenching, or after quenching, the result is that you see a large range of different morphologies and also quenching timescales in these simulations. So what's ahead of us, right? How can we make further progress? And I think it's really going on to the scales of spatially resolved studies also for quiescent galaxies, right? I have shown you that for star-forming galaxies, you're able already to measure color gradients and star formation gradients. But for quiescent galaxies, this is still very, very difficult or impossible, especially at high redshifts. But with ELT and GMT and maybe TMT, we will be able to start measuring gradients on the stellar population side, age gradients and quenching timescale gradients on a few hundred parsecs. And so this will really help us to understand how quickly galaxies will quench their star formation from the inside out. And then for me particularly, because I'm part of the NearCam GTO team, I'm very excited about the James Webb Space Telescope. You have heard of it. It will be launched at the end of this year. It's cool because it has a larger mirror, it can collect more light, but it also extends into the infrared further than HSD. So it will allow us to spatially resolve galaxies much better and also to really find the highest redshift galaxies and measure their terrestrial optical properties. So again, it's getting really real. So I know the telescope is now at the launch site, and so we're looking forward to the launch. And again, why is it so cool, right? Because we go currently from observations like this with Spitzer to observations such as those with JWST. So you will be able to find many more faint high redshift galaxies, and in particular also quiescent galaxies. And I'm happy to talk more about this and some of the surveys and progress we are currently doing on simulating these data sets. But I just want to highlight that there is, as part of the JADES team, we will follow up and we will basically produce images of exquisite depth for both QUIDS North and QUIDS South, and we will follow up these objects also with spectroscopy. And so I think this survey will really help us to lay the foundation for early universe science in the 2020s. And again, this is not just focusing on ionization and the highest redshift galaxies, but it really helps us to understand when did the first quiescent galaxies form, and also how the budge and disk components form that we already see present around redshift of 2. So let me summarize and come to the conclusions. I showed you that, when we look at galaxies that are star forming, and we believe that these are the progenitors of the most massive elliptical galaxies in the local universe. When we look at these star forming galaxies, we can see that they are quenching from the inside out, and we see some signature for black hole activity. When we look at the quiescent galaxies at redshift of 1, and we see that at redshift 1, there is already a substantial population of massive quiescent galaxies in place, we can see that there is a large diversity of galaxies. It's not that all quiescent galaxies are the same, but it seems that there is a large diversity of how quiescent galaxies, even at redshift 1, can form, over which timescale they quench, but also when they quench. And so this points towards a complicated process of quenching. It's not just one process, it's probably a combination of internal processes related to black holes, but also external processes which are related to how gas and also smaller galaxies merge onto these larger galaxies. And again, there is, of course, another 10 or 6 to 8 giga years of cosmic time where there is, of course, a lot of more mergers happen, and the formation of fast versus slow rotators will come into place. Something that I didn't have time to talk about at all. And I think the future is very bright. I think that we should make more progress on really timing quenching and measuring quenching timescales. And I showed you that we make some progress on making more careful comparisons between observations and theory by projecting the theoretical models into the observational space and redo the same measurements. JWST will be great to find the first quiescent galaxies, and ELT and GMT and so on will be great to measure spatially resolved quenching, because we will have the spatial resolution, but also the light collection area to basically measure the spectral indices to measure quenching timescales. Okay, yeah, thank you very much for your attention. I'm of course very happy to answer any questions, because I know I was probably quite quick over many of the topics.
Thank you very much, Sandro. So for the people on YouTube, we thank for your attention, and we expect to